So we're going to learn another test today. Good evening. So we're going to learn another test. It's called the alternating series test. So before I start, anyone has any questions? Let me take pictures, see who's on time. So we're going to cover 3 sections. The first one, we're going to use this alternating series. Remember, alternating series means one positive, next one negative, the next one positive, negative, positive, negative. So basically, we have a -1 raised by n. And sometimes, if an alternating series converges, we may be able to estimate the sum. And we will explain the meaning of absolute convergence and conditional convergence. So with alternating series test, we have 2 kinds. One is called absolute convergence. One is conditional convergence. So far, we have primarily discussed the series with positive terms. Remember, comparison test, limit comparison test, all require, we may ignore finite many terms. Remember the big capital letter N. So we can ignore some finite terms. But we require the terms to be positive, so can compare. In this section, we introduce alternating series. Those series whose terms alternate in signs, positive, negative. We will show in later chapter that this series often arise when studying power series. So next chapter, we're studying power series. After defining alternating series, we introduce alternating series test to determine whether such a series converges. So let's see this one. So this one is a geometric series, right? So the ratio is -½ And we know this series converges, right? And we can even calculate. And we see this one too. So this one is alternating series. So we get a 1 -½ plus 1/3 minus 1/4 plus 1/5, so on and so forth. So this looks like a harmonic series, but with -1 raised by n plus 1's power. So the definition of alternating series. Any series whose terms alternate between positive and negative value. Okay. And can be written in the form of -1 raised by n or n plus 1 bn. So we'll get b1 minus b2 plus b3 minus b4, so on and so forth. Or -1 raised by n, bn, then the first term will be negative. We'll have negative b1 plus b2, so on and so forth. Well, here, of course, the bn term are positive terms. So let's see the first one. So this one, right? -½ raised by n. So that's 511. So in 511 is a geometric series. And absolute value is absolute value of negative half, which is less than 1. So it converges. And 5.12, so this is called alternating harmonic series. Without negative 1 raised by n plus 1 is called harmonic series. With negative 1 raised by n plus 1, we call alternating harmonic series. So we will show that whereas the harmonic series diverges, but alternating harmonic series converges. All right. So harmonic series is a famous series diverges, but the alternating harmonic series converges. Of course, the first one converges as well. So let's see, consider the atom as 2k plus 1. So 2k plus 1 just forces this to be odd terms, right? So we have odd many terms. Add together, that's S2k plus 1. So S2k plus 1 equals S2k minus 1 minus the next term. The next term is 1 over 2k plus 1 over 2k plus 1. All right. And so minus 1 over 2k is bigger than plus 1 over 2k plus 1, positive 1 over 2k plus 1. So this term, those two terms will be a negative number. Those two terms will be a negative number. So that's why S2k minus 1 minus a number is less than itself. So this is saying the sum of 2k plus 1 is a decreasing sequence. Right? So let me read out those terms. So we got 1 minus half, plus 1/3, minus 1/4. So this is the alternating harmonic series. So on and so forth. And then we see each pair, we get a positive value. 1 minus half is half. 1 over 3 minus 1 over 4. That's 1 over 12, right? So on and so forth. So this 1 over 2k minus 1 minus 1 over 2k will be 1 over 2k times 2k minus 1. So each pair, if we do this, each pair gives us a positive value. So that means the sum is still a positive term. So which means the sum of 2k plus 1 terms is bounded below, because we want to use monotone convergence theorem. Since the sum of 2k plus 1 is a decreasing sequence that's bounded below by the monotone convergence theorem, so the sum of 2k plus 1 terms converges. Similarly, the even term as of 2k form an increasing sequence that's bounded above because this. Right? Sum of 2k terms equals to the previous term, 2k minus 2, plus the next term, which is 1 over 2k minus 1 minus 1 over 2k. And of course, this subtraction is a positive number. So that means S2k minus 2 plus a positive number is greater than itself. We can read out 2k terms, sum of 2k terms. That will be 1 plus negative half plus 1/3, so on and so forth, right? Because that's going to be 1 minus a number. 1 minus a number will be negative 1, because each pair gives us a negative number. Negative half plus 1/3, that's negative 1/6. Right? Negative 1 over 2k minus 2 plus 1 over 2k minus 1. That will be negative 1 over 2k minus 2 times 2k minus 1. Then minus another term. So this for sure is less than 1. So the sum of 2k plus 1 terms equals to the previous term plus 1 over 2k plus 1. So since each one, so S2k less than 1, right? Then those are finite numbers. So bounded below all finite numbers and is decreasing. So we could take a limit of this. When we take a limit, we get a limit of S2K, well, which is less than 1, a limit of 1 over 2K plus 1, well, when K approaches infinity, of course, this goes to 0. Right? So that proves the series converges. In reality, it converges ln of 2. Okay, it doesn't show. Okay, it doesn't show, doesn't prove it converges ln 2, but for now, let's just remember that, okay? So harmonic series diverges, but the alternating harmonic series converges to ln 2, natural log of 2. So this basically shows the picture of it. So in general, in any alternating series of form 3 or 4 converges. So let's go back to, so those two, right? If we have alternating series like this, they converges. So the proof is similar to the proof for alternating harmonic series. Okay, theorem, alternating series test. Now, alternating series of the form, so sum of infinite many terms, -1 raised by n plus 1. So we do n plus 1, -1 raised by n plus 1 is to force the first term to be positive. Right, because n start with 1, 1 plus 1 is 2, -1 squared, which is positive. So this forces the first term to be positive. Or the second one, or this one, right? This one is the first term to be negative. So -1 raised by 1, still negative. So this is the first term is negative, this one, the first term is positive. So it converges under conditions of those two. So first is decreasing sequence. Okay, so Bn plus 1 less than or equal to Bn. Okay, or non-increasing, because less than or equal to means non-increasing. Okay, non-increasing. So first is non-increasing series and also positive. Okay, the terms are positive. And second, limit of a term equals 0. Because it's decreasing, right? As we can imagine, it decreasing, at a certain point, it decreases to, because it keeps decreasing. And then to keeps it decreasing, and at a certain point, it will approach to 0. So satisfying those two conditions, all right? All terms are positive, so not including -1. Okay, -1 forces it to be alternating, but Bn itself is positive, right? So Bn itself, so which means absolute value of the series, right? Only consider Bn, not considering -1, not considering the -1, the alternating signs. So Bn itself is a decreases. And the limit of nth term goes to 0. when n approaches infinity. Okay, this is known as alternating series test. The first one, right, the condition, each term is positive and it decreases. Okay, the second one, the limit of nth term as n approaches infinity goes to 0. All right, let's see an example. Again, this is saying we can ignore some terms. Up to capital letter N, up to, basically this is saying we can ignore the previous terms. If finally the series goes into non-increasing, all right? So the first n terms may be increasing, but after the n terms, the rest of it is non-increasing, all right? So we can always ignore finite many terms. Okay, let's see these two examples. The first one is -1 raised by n plus 1. So forces the first term to be positive over n squared, right? This is alternating p series, right? P equals to 2. The second one is -1 raised by n plus 1. Again, forces the first term to be positive, n over n plus 1. So let's compare the nth term and n plus 1 term. So the nth term will be 1 over n squared. The n plus 1 term, we ignore, okay, the two conditions. The first condition, we don't consider the signs. We don't consider the sign, positive or negative. We just compare the absolute value of it. So 1 over n plus 1 squared is less than 1 over n squared. So it's decreasing. The terms decreases, right? Ignore the sign. And also the second condition is the limit of nth term 1 over n squared as n approaches infinity, 1 over n squared approaching 0. So two conditions satisfied. So two conditions satisfied, that is to say by alternating series test, this series converges. So the series of A converges, right? This is for all P series, converging P series. So this is P equals to 2. You can say P equals 3, P equals 4, so on and so forth, as long as P greater than 1. So alternating P series for P greater than 1 converges. Or you can think from another way, right? P series converges. P series means every term is positive or non-negative. Non-negative. And here we have negative terms. So this series, alternating P series, is less than P series. P series converges, right? The less than P series must converge also. So we can prove from another point of view. And we can prove from this point of view by alternating series test. So the first condition satisfied is a non-increasing, the terms are non-increasing. Actually, the terms are decreasing. And second, the limit of nth term goes to 0 as n approaches infinity. So by alternating series test, this series converges. Anyone has any questions? Okay, let's see B. B, n over n plus 1. So since n over n plus 1 not approaching to 0 as n approaching infinity, so the second condition does not satisfy, right? So limit of this approaches 1 when n approaches infinity, so it's not 0. So the second condition does not met. Second condition is not satisfied, so we cannot apply the alternating series test. Instead, we use the nth term test for divergence. All right, remember divergence test? We use nth term test for divergence, since the limit of this nth term not equal to 0, so the series diverges. Right? That's a divergence test. Right? If the nth term not going to 0 as n approaches infinity, the series diverges. So basically saying, it's the nth term as n grows to be bigger and bigger to infinity, and the term still have some value, still not vanishing. So that adds up to infinity. Right? So that's a divergence test. Any questions? Okay, checkpoint. So let me show you these two conditions one more time. We have alternating series, right? The first condition is we require terms itself, ignore the negative, the signs, non-increasing, right? Non-increasing. And second, limit of nth term is 0. So we need the two conditions to apply alternating series test. All right, so your turn now. Try checkpoint 5.18. Okay. Yes, we're doing 5.18. Okay, we're doing 5.18. Please try 5.18. So we want to use alternating series test. So basically, we want to check the two conditions are satisfied by this. The first condition is to prove the absolute value of the term non-increasing, or even better, decreasing. And second, we want to prove the limit of nth term goes to 0. If those two conditions are met, we can conclude the alternating series converges. Right, so we should try. So we need to confirm two conditions. The first condition, convergent. Let's see. Okay, most people vote for convergency. So Bn equals to, so let's write down. So Bn equals to n divided by 2 raised by n. Right, that's Bn. Or let's compare with n plus 1 divided by 2 raised by n plus 1. So we compare those two terms, right? N over 2n and n plus 1 over 2n plus 1. So n over 2n, n plus 1 is a linear change, right? We know linear function, constant change. But 2 raised by n is exponential change, it doubles. So the bottom is exponential function. The numerator is a linear function. So it grows, the denominator grows much faster than the numerator. So which means this is a decreasing, right? So the n plus 1 term less than or equal to n term. So this is saying, so the first condition is met, right? The first condition needs the terms non-increasing. Second one, we'll take a limit. So when we take a limit as n approaches infinity, n over 2 raised by n, right? As n approaches infinity, again. So how do we do this limit? We use the L'Hopital's rule, right? We take the velocity of each function. We take the derivative of each function, which measures the velocity, measures the rate of change. So rate of change of linear, so derivative of n just 1. The derivative of 2 raised by n is 2 raised by n ln 2, right? So again, the denominator grows much, much faster than the numerator. So indeed, nth term goes to 0 as n approaches infinity. So indeed, by alternating series test, this series converges. Anyone has any questions? So 2 steps. First step, we compare n term and n plus 1 term to prove it's non-increasing. Second step, we take a limit of nth term, and we show limit of nth term as n goes to infinity, the nth term goes to 0. Then we conclude by alternating series test, this one converges. Anyone has any questions? Okay. Let's see this theorem. It's called remainders in alternating series. Consider an alternating series of the form, right? First one to be positive, first term to be positive, or first term to be negative. That is satisfying the hypothesis of the alternating series test. Let S denote the sum of the series and Sn denote the nth partial sum. For any integer n greater than or equal to 1, the remainder Rn equals S minus Sn satisfies the remainder, the absolute value of the remainder is less than or equal to the n plus 1's term, absolute value of, just ignore -1 sign. Okay. Okay, this one is not too important for us. Let's use that to see this one. So we have this series where the alternating p series with p equals to 2. So use the remainder estimate and to determine a bound on the error R10 if we approximate the sum of the series by the partial sum S10. Okay, so this is saying the remainder is bounded by the next term. Okay, so R10 is bounded by B11. So we just use that. So B11, that's just 1 over 11 squared, right? So R10 is bounded by this. Alternate is bounded above by this. All right, let's absolute, okay. Conditional convergence. So absolute convergence, conditional convergence. So consider a series of an, sum of an, and the related series, absolute value of an. So an itself can be positive, can be negative, right? Absolute value of it, they are related. So here we discuss possibilities for the relationship between the convergence of those two series. For example, consider alternating harmonic series and harmonic series itself. So the series whose sum absolute value of this term is a harmonic series, and the harmonic series diverges. But alternating harmonic series converges to Ln2. Since the alternating harmonic series converges, but the harmonic series diverges, we see that alternating harmonic series exhibits conditional convergence. Conditional convergence. By comparison, consider the series alternating P series with P equal to 2, the series whose terms are absolute value of the terms of the P series with P equals to 2. Since both of these series converges, so we see that this series, alternating series, exhibits absolute convergence because it doesn't matter, right? The alternating one convergent, without the negative ones involved, without the signs involved, it converges, right? It's called absolute convergence. Like harmonic, right? Without signs involved, what absolute value of that is a harmonic series, it diverges. But the alternating series converges. So that's a conditional. So that's conditional convergence. If the absolute value of the term of the series converges and the alternating one also converges, we see that's absolute convergence. Because the sign doesn't do anything, right? The first one, the sign does change the divergency to convergency. But the second one, the sign doesn't do anything to it. So it's absolute convergence. Definition. A series exhibits absolute convergence if its absolute value converges, just like the second example, all right? The P series, alternating P series. Absolute value of it is just a P series. The P series converges, alternating P series converges, so it's absolute convergence. A series exhibits conditional convergence like alternating harmonic series, right? It's if the series converges, but absolute value of it diverges. It's called conditional convergence, convergency. For example, is alternating harmonic series converges, but harmonic series diverges. So absolute convergence implies convergence. All right. If absolute value of series converges, then the alternating one converges. All right. So you can see from those two, right? The second one, right? 1 over n squared is absolute value of -1 raised by n plus 1 over n squared. So it converges. So, because the alternating one is always smaller than the absolute value one, right? Alternating one will have plus, minus, but absolute value of it just all positive, right? So of course, yeah, if the bigger one converges, the smaller one converges. So absolute versus conditional convergence. For each of the following series, all right, let's try that. So A will have -1 raised by n plus 1, so the first term is positive, over 3n plus 1. B will have cosine n over n squared. So we take absolute value of the term. Absolute value of the terms is 1 over 3n plus 1. Right? If we can prove this one converges, then we can see the original alternating series converges, right? Because this is a bigger series, 1 over 3n plus 1. But this one, if we use a limit comparison test with a harmonic series, so we see it diverges because use limit comparison test, we get a value, get a 1 over 3, right? So if the limit of the ratio equals a finite number, not 0, we see the two series are related. If one converges, the other one converges. If one diverges, the other one diverges. So limit of the ratio equals 1/3. So the denominator one diverges, harmonic series. So we can conclude the numerator one diverges also. So the absolute value of that series diverges. Okay, so we can conclude this alternating series does not converge absolutely, but maybe converges, conditionally. So let's use alternating series test, right? We see if the two conditions are met. So the n plus 1 term is 1 over 3n plus 1 plus 1. So this is the n plus 1 term. And this term, the denominator is much bigger than 3n plus 1, right? So the whole thing is less than 1 over 3n plus 1. So this means it decreases, the term decreases. Then when we take a limit of the nth term, it does go to 0. Okay, two conditions met. So two conditions are satisfied. We can conclude by alternating series test, this series A converges. All right, series A converges, but it converges conditionally because the absolute value of it diverges. So this is a conditional convergence. So we conclude this series converges conditionally. Okay, anyone has any questions? All right, keep moving. Let's see B. We know cosine functions. Sine, cosine is bounded below by -1, is bounded above by 1. Right? We want to determine whether this alternating series, or no, this is not alternating series, but it is alternating because cosine is, is between -1 and 1. So even we don't see negative signs, but cosine n can be negative, can be positive. Oh, where did it go? So we want to compare this one with 1 over n squared with P series, right? With P series, because we know P series converges. Well, let's see. So we want to compare with series P series when P equals to 2. Since P series when P equals to 2 converges by the comparison test, absolute value of this converges, right? Because we can take a limit, right? We can take a limit of the ratio, so cosine n over n squared divided by 1 over n squared, we just get cosine n, absolute value of cosine n. So absolute value of cosine n divided by n squared converges, and therefore the original cosine n divided by n squared converges absolutely, right? Right? Because the bigger one converges, absolute value of cosine n over n squared converges. That forces cosine n to be positive. But the original one, cosine n, can be negative, can be positive. So this is a smaller series. So the bigger series converges. Of course, the smaller series converges as well. So this one converges absolutely. Anyone has any questions? All right, let's all try 5.20. Let's try 5.20. It's an alternating series. We want to show if it converges absolutely or converges conditionally, or it doesn't converge at all. Okay. Kelly's not here either. Okay. 1950. That is here. All right. Okay. Converges absolutely. Converges absolutely. All right. So if it converges absolutely, that means the absolute value of it converges, right? So we have n over 2n cubed plus 1. So what do we want to compare with? We want to compare with n over 2n cubed. And we see that's P series. Right, that's n over, we could just do n over n cubed or 1 over n squared. We can compare with that. And we show, well, that's P series with P equals 2 converges, so this equals 2. If you take a limit of that, we use a limit comparison test, we will get a number. So that is to say the absolute value of this series converges. Right? Then that means this one, alternating one, is a smaller one. It converges absolutely. We don't have to do more. All right. For absolute value convergency, all we have to do is to show absolute value of the series converges, and that's it. If absolute value does diverge, we want to do more. We want to use alternating series test. We want to check the two conditions. But for this one, yes, it converges absolutely. Let's see if we get example of converges conditionally. Not really. Okay, let's go back to the alternating harmonic series again. So this is to show that series converges to Ln2. It says let's rearrange the terms, right? So let's do half of it. So if we multiply by half, so we get the first term to be half, second term to be negative quarter, then third term is 1 over 6, and so on and so forth. Right? Oh, okay, so this is using Ln2, So get Ln2 divided by 2, so we want to use the alternating harmonic series equals to Ln2 to rearrange the terms in the alternating harmonic series. So the sum of rearranged series is 3 Ln2 over 2. Okay, I don't care. All right, so that's alternating series test. So next class, we're going to talk about ratio and root test. All right. And then when we finish that, we're going to power series. Okay, so let's see. So I don't want to go to ratio and roots. I think we have enough time not to cram in everything. Let's see, we have, so today's Thursday. So we have next month, next Tuesday, next Thursday. We can cover ratio and root test on Tuesday. And then we're going to power series on Thursday. And so Thursday, maybe we can talk about 6.1, 6.2, 6.3, because mainly in chapter 6, we're going to cover two series. One is called the Taylor series, another one is called the Maclaurin series. So that's for chapter 6. Maybe we needed 2 or 3 classes. So after we finish, so once we get into power series, so we have, then spring break. So April 18 to 22 is spring break. So April 19, April 21, we won't have class. Then when we come back, we have April 26, April 28, 2 classes. And May 3rd, May 5th, and May 10th, and May 12th. Okay, so we have enough time. So we use 2 or 3 classes to cover power series. Then we get into chapter 7. Chapter 7, we're going to talk about parametric equations. calculating curves and polar coordinates. That probably would take 3 or 4 classes for chapter 7. Okay, that's good. So today, so we won't talk more today. So I'm going to assign you homework from this. Okay, so that's it for today. Anyone has any questions? So we can finish earlier today. Any questions? Was attendance taken? Just want to make sure. Yes, I did. I did take attendance already. Okay, so anyone has any questions? Reminder to anyone who hasn't finished today's homework. It's my not a Blackboard. Oh, sorry, Paul. So that means I forgot to post on Blackboard, right? Oh yeah, my bad. We're skipping the other section in chapter 5. Chapter 5. No, we're not skipping. Chapter 5, we're going to finish chapter 5. Chapter 5 will have one more, ratio and rule test, which we'll talk about next class. Chapter 5 not going to be skipped. Golem, you're starting to hate math. Why? You're not getting the series, the sequence stuff. Good night. So just different concepts. All right, it's just different constructors. So sequence, series, there's different constructors. In the future, you know, are they really useful? Not so. They can be useful, but not as useful as functions. Don't hate math. Okay, Golem. Not because of series and sequence.